Welcome back. It's good to see your happy, smiling faces. This is Chapter 15. We'll be talking about mechanical waves. Starting off, we'll talk about the properties and types of mechanical waves. We'll talk about some of the nuances of waves, speed, frequency, and wavelength. Introduce waves mathematically, talk about speed and energy of mechanical waves. Very important, we'll talk about how waves can interfere with each other and analyze standing waves on a spring. And lastly, talk about stringed instruments. So why exactly do we care about waves? Well, it turns out that waves are everywhere, from earthquakes to musical instruments. And really what we're interested in is how can we use physics to interpret these waves. There's going to be two types of mechanical waves that we're going to talk about, and we'll say that a mechanical wave is a disturbance traveling through a medium. We're going to talk about first transverse waves and then longitudinal waves. For longitudinal waves, I don't really care for the pictures in the book. I think that having a big mean bully at the end of a line is much more representative of at least physics. This big mean bully is going to give a shove to the person in front of them. That person's going to run into the person in front of them, run into the person in front of them, and so on and so forth. There's going to be kind of a chain reaction here. So you're going to see kind of a pulse go from the bully to the poor kid at the front of the line. We're going to see the wave travel in that direction. Now, if I think about these individual children as particles, they're going to be moving essentially back and forth as the wave transmits in the same direction. So for longitudinal waves, the key idea is that the particles and the waves are in the same direction, are moving in the same direction. An example of this that is relevant to you right now is actually sound. If you think about what is sound, well, here you have the speaker of an old school boombox, where this could be the speaker of your computer carrying the relentless drone of my voice. Now, inside of that speaker is going to be a membrane, and this membrane is going to vibrate back and forth. What that guy is doing is it's moving the particles in the air back and forth. So the particles are moving back and forth, and the wave is going to be transmitted away from the boombox. The interesting thing here is that these particles, while they are moving back and forth, one individual particle does not start out at the speaker and work its way all the way to your ear. It's the motion of that particle that bumps into the particle next to it, that is going to carry the energy that is associated with the wave. If you think about it in terms of pressure, there's going to be regions of high pressure and regions of low pressure that are vibrating back and forth, carrying this longitudinal pressure wave to your ear. One thing to note is if you think about all those Star Wars and Star Trek movies, this needs air to exist, or this needs air to work. This will not work in a vacuum. So when you see the laser go off in Star Wars and you hear a neat little dejou or something like that, really the physics doesn't support that. For transverse waves, if you think about people doing the wave as the mascot goes by at, say, a football game and they've had several beers, the way that it works is the mascot is going to run across the room or across the field, and this person's going to go up, and then this person's going to go up, and then this person and this person and this person, and meanwhile this person's going to sit down, sit down, sit down, sit down. In this case, let's think again of these people as particles. These particles are moving up and down. The direction of the individual particles is up and down, however the wave is in the perpendicular direction. So that's kind of a definition of a transverse wave. So let's take a closer look at a transverse wave here. Suppose I have a string and I attach my hand to this end and I swing my hand up and down essentially in periodic motion. What that means is I'm going to set up a wave on this string, and you can see that the wave is going to essentially propagate across the room. just getting some semantics out of the way here, if I look at the distance from the equilibrium point up to the largest point or to the lowest point, I'm going to define that to be the amplitude. And really, the larger the amplitude, the more energy it's going to carry. The wavelength, that is going to be the distance from one peak to the next peak, and that's going to have the Greek symbol lambda. Frequency, if you think about maybe an observer over here on this side of the room, that's going to be how many cycles are going to pass in a given time, where one cycle is the distance from one peak to one peak. As in the last chapter, the frequency, or the last chapter, chapter 14, the frequency was also related to the period of this, which is simply by an inverse. The most important equation on this slide is going to be the wave speed, so it's going to be the wave velocity really, and that's related to the frequency of the wave as well as the wavelength. Kind of looking at this guy, we can see that the wavelength is going to have a unit of distance, or meters. Frequency, we know that that's going to have it units of 1/seconds, and of course velocity is going to be a meter per second. We can come up with the same definition for longitudinal waves. If I have a plunger that's oscillating in a piston in simple harmonic motion, it's going to have regions of compression and then regions of low pressure. And really the wavelength is going to be the distance from one region of, let's just say, low pressure to the next region of low pressure. And of course the wave is going to propagate in that direction, and the regions of high and low pressure are going to move in that direction. You can kind of see here how it tracks the crest as it moves from one side of the screen to the other, and the amplitude is going to be how much compression relative to how little compression there is. But all of the definitions from the previous slide still hold for these waves. It's just a little bit harder to visualize.
Graphing it,
So let's talk about how we describe a wave mathematically. You may recall that we previously talked about waves being sinusoidal, and we talked about them only in time. However, if we now look at a wave that is propagating at some distance, we also need to consider the position of the wave. So here we have an oscillator, and we're going to start it off at its amplitude, and we're going to essentially shake it up and down in simple harmonic motion, and we're going to describe it with the wave function, which is going to depend on both the position and the time. Now the way that the book started theirs off is they started it off at the maximum amplitude, so they're going to describe it using a cosine. However, it could just as easily be described using a sine term. So the position is going to be equal to the amplitude multiplied by cosine. Cosine is going to vary between -1 and 1, and multiplying it by the amplitude lets us reach any amplitude, any position that we can reach. It's going to depend on omega t, which you're familiar with from chapter 14. Remember that the angular frequency here is related to 2 pi multiplied by the linear frequency, which is also related to the period. And then the new term is going to be this kx term, which is called the wave number, and that's simply going to be equal to 2 pi divided by the wavelength. So very, very important to be able to recognize and use these equations to convert back and forth between frequency, angular frequency, and wave number. Now, if we take a look at graphs of the wave function, the key thing to remember is what is along the y-axis here. Is it position or is it time? They're both describing the same thing. Suppose I'm talking about my hand that I'm moving up and down. If I looked at that as a function of position, then I can say that my hand at any given time or at any given position is at any given y position. If I looked at my position versus time, then I'm describing where my hand is at any given time. The key difference is if we look at the distance from peak to peak on either one of these two graphs, it's going to have a different physical meaning. On a position versus y versus x graph, we're talking about the particle's wavelength. For the position versus time graph, we're talking about an object's period. Again, the period is related to the frequency with an inverse relationship. Now this fun little chart right here shows you kind of graphically what the velocity and acceleration are for a wave. Suppose I took the end of a rope and I whipped it up and down. We can see at point number 1 here, this wave is going to have a velocity, the particles are going to have a velocity in that direction, but they're going to be accelerating back towards the equilibrium position. At point number 2 here, the object is not going to be accelerating, but the particles are going to have a velocity in the upwards direction. For number 3, it's going to have a velocity in the upwards direction and an acceleration in the upwards direction, and so on and so forth. Note, however, that all of these velocities are going to be the velocities of the individual particles, which is going to be different than the velocity of the wave. This is a transverse wave, so the velocity of the wave is in that direction, and the particles are moving in the up and down direction. The part number B here simply shows this is going to be what the wave looks like at some time later. So let's talk really quickly about the speed of a wave on a string. Suppose I have a string and I send a pulse down that string. How fast is it going? The book goes through the big gory derivation. You get to see some really cool partial derivatives. I highly advise you to check that out if you'd like to. Really, at the end of the day, what it boils down to is the speed of the wave is going to depend on two things. It's going to depend on the force. Very often this is just going to be the tension on the string, and it's also going to depend on the mass, or in this case this is actually going to be the mass per unit length. And if you think about tuning a guitar, you have different strings. They have different masses per unit length. You have some big fat ones and some skinny ones. What you're adjusting when you adjust a guitar, you're adjusting the tension, which is going to be changing the speed of the wave as well as the frequency. In example 15.3, we get to use this guy. They have a geologist at the bottom that has loaded up about 20 kilograms of samples, and they shake the rope back and forth at a rate of 2 hertz to alert their buddy up on top to start pulling up the sample. And we're asked for two things. We're asked for, in part A, what is the speed of the wave, and in part B, what is the wavelength. So the speed of the wave is going to be equal to the tensional force divided by mu, which is going to be the mass per unit length. So the tensional force is going to be the 20 kilogram box multiplied by gravity, 9.8. So 196 newtons. The mass per unit length is just going to be mass per length. This is of the string. That's going to be 2 divided by 80, or 0.025 newtons per meter. So the speed then is just going to be 196 divided by 0.025. Go ahead and take the square root, and we get 88.5 meters per second. For part B, I know that the speed of a wave is equal to the wavelength multiplied by the frequency. Therefore, the wavelength must be equal to the frequency divided by the speed. Scratch that. The speed divided by the frequency. So 88.5 divided by the 2 hertz is going to give me a wavelength of 44.3 meters. Now, in a more advanced physics class, you'd say, wait a minute now, the rope actually has mass, and so the tensional force is actually going to be changing as we work our way up and down this rope. So, in reality, it's actually a little bit more complicated than what example 15.3 leads us to believe. Now, we know that waves are going to transmit energy. That also means that they're going to transmit power. And it turns out that we can write their maximum power as the product of first the square root of their average mass multiplied by the tensional force in, say, the wire, multiplied by the frequency squared multiplied by the amplitude squared. And this relationship is going to be true for all waves. The interesting thing here is that the power is going to depend not only on the amplitude of the wave, but also on the frequency of the wave. So we can increase the power of a wave simply by increasing the frequency. Also, what's interesting is, suppose we double the amplitude of a wave, it's actually going to quadruple the power of the wave. Since this is a sinusoidal function, the average power will always simply be 1/2 of the maximum power. It's often a lot more useful to talk about the intensity of a wave, which is going to be equal to the average power divided by the cross-sectional area of the wave. Now, I used to work in lasers, and in that case we had a highly collimated source. It's not changing its area over time, so we would often say that the intensity was just going to be the power multiplied by the cross-sectional area of our laser beam. If we're talking about point sources, however, think maybe your car's stereo or something like that. It has some power associated with it, and it's going to be radiated in all directions. In that case, we would say that the intensity is going to be equal to the power divided by the cross-sectional area of the sphere that is sending waves out in, which is going to be 4 pi multiplied by the radius squared. So that's a p right there. It's kind of interesting because we can say, well, suppose I look at this first radius r1 here. My intensity here is going to be 4 pi, the power divided by 4 pi r1. If I looked at some new radius, that is going to be the power divided by the cross-sectional area of that sphere, 4 pi r2 squared. And out here we know, if you get further and further away from a loud car stereo, it gets less and less and less intense. The power of the wave, the power of the radio has not changed. However, the radius has changed. So we could even say that the intensity at 1 multiplied by the radius at 1 squared must be equal to the intensity at 2 multiplied by the radius at 2 squared. So the radius goes up, the intensity must go down, at least for spherical waves.